Good morning, it's Shannon coming to you live from San Diego. I teach at Maricosta College and I'm making these videos for my wonderful discrete mathematics class. So today we'll be learning about indirect arguments and specifically contradiction and contraposition. These are some of my favorite kinds of proofs and very useful, so let's check them out. Now, let's say somebody stole a car, right? Exactly at 10 p.m. from the Walmart parking lot in Oceanside on February 27th, 2019. And the police decided to arrest you. So what have the police done? They have made the assumption that you committed the crime, but in order to commit that crime, it would have to be at that time and place, right? So if we kind of restated that, if you committed the crime, then you would be located at the Walmart parking lot at 10 p.m. on February 27, 2019. So recall with the contrapositive, if you assume not Q, right? Or if you can show not Q, then not P, then basically you have shown that it's a false assumption. All right? So that's one of the things that we're looking at today. Not that you've committed any crimes, but just that kind of logic. Okay, so ready? Here we go. Method of proof by contradiction. What you want to do is suppose or set it up where the statement to be proved is false, right? So that is, how do you suppose that? Well, you negate the statement. So you suppose that the negation of the statement is true. And then, of course, you have to show that this supposition leads logically to a contradiction. And then once it leads to that contradiction, we have shown that the original statement is true, right? So then you conclude that the statement to be proved is true. All right? So here's a theorem that lends itself to that kind of proof. There is no greatest integer. So remember how your teachers are always saying, why are you putting brackets around infinity? Well, because infinity is just an idea, right? It's a direction. It says that this trend continues without end. So we don't really write infinity with integers, right? That's more of an interval notation thing. But it's kind of a similar idea. There is no greatest integer. So some people actually will state proof by contradiction, if that's what they're going to do. So let's just go ahead and write that, or you could just start with proof. All right, so what would our negation to that be? Well, we could suppose there exists some n which is the greatest integer. So that's why we're giving it capital N, all right? It's the greatest integer. Well, all the other lowercase integer n's, right, would have to be what? Good. Then n would have to be greater than or equal to all of the other integers n. So for any n belongs to the set of integers, right? But what do we know about integers? We know that they have closure, right? Under addition. So why don't we let m equal to capital N plus 1? Well, what is m? M belongs to the set of integers. And what is that from? Awesome. Closure. And so what have we done? We have shown the contradiction. Which contradicts n greater than or equal to lowercase n for any n belonging to z, the integers, right? The set of integers. So there does not exist, actually we'll say therefore, there does not exist a greatest integer. And we're done. Cool, cool? All right. So, moving on, here's another kind of cool theorem. There is no integer that is both even and odd. Okay, well, what do you think? It'd be pretty hard to do a proof directly on this, right? So proof by contradiction would give us what? What would our statement be? Our supposition. Beautiful. Suppose there does exist some n that belongs to the set of integers, which is both even and odd. Cool, cool? All right. Well, by definition of even, right, there's going to exist a k that belongs to the set of integers such that n is equal to 2k. Well, there's also going to exist, call it L, some L that belongs to the integers such that n is equal to 2l plus 1, right? That's by definition of odd. So what do we have? Good. 2k would have to be equal to 2l plus 1 because we're supposing that there's this integer n, this specific integer n, that is both odd and even. So if we isolate the 1, so subtract 2l from both sides, we would get 2k minus 2l is equal to 1. And then factoring out a 2, we would get a k minus l remaining, and that's equal to 1. And then isolating k minus l, we would get 1/2. All right, well, what is k minus l? K minus l has to belong to the integers because of what? Awesome. Closure. If you subtract 2 integers, you get another integer. So, we also got that k minus l was equal to 1/2, which is not an element of the integers, which is a contradiction. So, therefore, there does not exist an integer that is both even and odd. Groovy? All right. Next theorem. I know you're just as excited as I am. The sum of any rational number and any irrational and I guess I should have said number as well, is irrational. Okay. Well, again, we'll do a proof by contradiction. So, what would we suppose? There exists a rational number R and what's the definition of rational number, right? R would equal to some A over B, right? Such that A and B belong to the integers and B has to not be 0. And that's by definition. And let's also suppose there exists some irrational number S and let's further suppose their sum is capital S equal to, what do you want it to equal to? Beautiful. Maybe C over D, such that C and D belong to the integers, and what has to also be true? Such that C and D are also elements of the integers, and good, D is not equal to 0. So let's check it out. R plus lowercase s is equal to capital S. And R is what? A over B plus S is equal to C over D. And remember, that's just by substitution. And then continuing, we want to isolate S, right? Because the contradiction will be that S ends up being something that is a rational number, but S was given as irrational in the premise. So, isolating S, we have C over D minus A over B. And then, using a little algebra, we'll get a common denominator of B times D. And then we'll have BC minus AD. So let's check it out. The numerator, BC minus AD, belongs to the set of integers, and that is by closure. When you multiply two integers, you get an integer, and when you subtract two integers, you get an integer. And what else do we know? BD belongs to the integers, again, by closure. What else do we know? We know that D is not equal to 0, and B was not equal to 0. So AB is not So the product B times D is not equal to 0. And remember, that's by that zero product property that we learned. Thus, S is rational, which is a contradiction. Therefore, what can we say? The sum of any rational and irrational numbers is irrational. Cool? All right. So the next step is to take a look at method of proof by contraposition. So first off, it can help to, express the statement that you want to prove in symbolic form. So for any x that belongs to some domain D, if P of x, then Q of x. Because then you'll know how to negate Q of x. So second step would be to rewrite the statement in the contrapositive form. Well, what is that form? For any x in D, if Q of x is false, then P of x is false. And remember, that's logically equivalent, right, to the first statement. So then we prove the contrapositive by a direct proof. So, suppose x is a particular, your author emphasizes this a lot. People don't generally write this in proofs, but you need to know that when you're supposing, n belongs to the integer or x belongs to the real numbers or something like that, it's a particular and, but arbitrarily chosen element of the domain, because any element of the domain needs to work if a theorem is to be true. So, particular but arbitrarily chosen element of D, such that Q of X is false. And then that next step is you need to show, given that Q of X is false, that P of X is also false. And that proves the original statement. So let's look at this next proposition. And what we're going to do with this guy is we're going to prove it both ways. All right? Because there's not only one way to prove things. So this proposition is for all integers n. If n squared is even, then n is even. Look familiar? All right. So proof by contraposition. So what is the Q part? The Q part, this is like the Q of X, is here, right? The P of X is here. So we need to suppose the negation that n is even. So why don't we suppose n is odd? Right? Well, if n is odd, then there exists some k belonging to the integers such that n equals 2k plus 1, right? Well, what will we have? N equals 2k plus 1. That's by substitution. So if I square both sides, I'll get n squared is equal to 2k plus 1, that quantity squared. And then completing out that square, we get, remember you square each end, and then you double the product of the ends, getting 4k. All right, so now we need to show that this is odd, right? Because that would be the negation of P of X. If you factor out a 2 from the first two terms, and then that plus 1 is still hanging out, what happens? Now you just need to show closure, right? So 2k squared plus 2k belongs to the integers. And why is that? Closure. Probably getting tired of that one, huh? All right. Thus, n squared is odd by definition, right? Definition of odd. And we're done, right? If you want, you can clean it up and you can say, therefore, for any n belonging to the integers, if n squared is even, then n is even. Groovy? All right. So now, actually, I think that's probably the easiest way to do that particular proof. But you can use the quotient remainder theorem also. And you set the divisor equal to 2. So let's also do this proof by contradiction and check it out. So, suppose, what would we be supposing? Well, there exists some n, and what is n? It's an integer, so it belongs to the integers. such that n squared is even, right? Because you want the premise to be the same. And n is not even, right? We know that any integer must be even or odd, okay? And what is that by? That's by the quotient remainder theorem. I'll just say Q-R theorem with D equal to 2. All right, well, what does that give us? Since n is not even, n must be odd, right? So there's going to exist a k that belongs to what? Should be getting used to this by now, the integers, such that n equals 2k plus 1, right? All right, well, if n is equal to 2k plus 1 and we square both sides, we would get n squared is equal to 2k plus 1, the quantity squared, which is equal to 4k squared plus 4k plus 1. And then that in turn is equal to, I'll factor out a 2 from the first two terms, and we'll get 2k squared plus 2k plus 1. Well, like before, 2k squared plus 2k belongs to the integers by closure. Thus, n squared is odd, which contradicts our premise, right? Cool, cool. So, what do we say? Therefore, for any n belonging to the integers, if n squared is even, then n is even. And we're all done. Cool, cool? All right. All right. So let's do an example. Another, the other proofs are in your book. I feel like I'm not doing my job if I don't prove them, but I'll do. I think I have 2 examples from the book. So here, now, let's check this out. We need to decide, and this is sometimes the hardest part. We need to decide if something is true or false, right? And so you can play around with some real numbers, but remember, at the end of the day, you're going to have to do things that are in general. And that's why they always say that things are arbitrarily chosen. So this one, okay, if a sum of 2 real numbers is less than 50, then at least one of the numbers is less than 25. Well, that makes sense to me, right? Because if you do 25 plus 25, you get 50. And 50 is not less than 50, right? It's equal to 50. And And as you go higher, you'll get things that are greater than 50. So, okay, how do we want to do this proof? Do you want to do it by what? Why don't we do proof by contraposition? So, suppose, what do we need to suppose? We're talking about the real numbers now. So, what do you want to use? A and B maybe belong to the real numbers such that A is greater than or equal to 25 and B is greater than or equal to 25, right? So remember, with contraposition, our if statement, our P of X, if you will, is the premise. And then our conclusion is our Q of X, and we're negating Q of X. So the negation of at least one would be that both are greater than or equal to 25. So, all right, if this is true, A plus B is going to be what? Greater than or equal to 25 plus 25, right? But what's 25 plus 25? It's 50. Good so far? So, therefore, if a sum of two real numbers is less than 50, then at least one of the numbers is less than 50. Oh, sorry, less than 25. Cool, cool? All right, so last example. If A and B are rational numbers, B is not equal to 0, and R is an irrational number, then the sum A plus B times R is irrational. So let's do this one by contradiction. Now remember, whenever you're dealing with rational numbers, you always want to be thinking of, okay, I got to write it in the form of A over B or M over N or something like that, where, you know, those components are integers. So that's just something that you're going to have to be used to using as we go through the rest of the class here. So here we go. What do we have to do? What's our setup? If we're doing this by contradiction, remember that the premise, which is all of this, right, is the premise. That has to be true, right? And we suppose that this part, that the negation of this is true. So This is our conclusion. So you don't mess with the premise, all right? But you suppose that the conclusion is the negation of it. And then you try to find a contradiction. All right, so let's do it. Suppose there exists. So what do we have? We have A and B are rational numbers. So an A and B, which are rational numbers, B is non-zero, and R is an irrational number. Good so far? There's going to have to exist, I don't know what you want to use. We have a lot of letters going on here, right? I guess we can use I and J and stuff. All right, so there exists an I, J, K, and L, which belong to the integers, right? Such that J is not equal to 0, and what else wouldn't be equal to 0? L is not equal to 0. So if we let A equal to I over J, B equal to K over L. Oops. Guess I need to actually write what I'm saying. K over L. And then, all right, what else are we going to need? We're going to have this sum, right, too. So why don't we let capital S equal to M over N, such that M and N belong to the integers and N is not equal to 0. And you know what? If you forget something along the way, that's fine. You can always add it in. All right? So, all right. Let's also note K cannot be 0 since B was given to not be 0. We'll be using that in our plan here. Okay, so let's figure this all out. Let's add this stuff up. So we have A plus B times R is equal to this sum. Well, what did we call A? We called A I over J. What did we call B? K over L. We still have R as R. And then S was what? Beautiful. M over N. And that was all just by substitution. So, again, what do you think we want to do? We want to isolate R because our R was given in our premise to be irrational, right? And so if we show that you would get a rational result for R, then that would be our contradiction. So let's do it. If I subtract I over J from both sides, I'll get K over L times R is equal to M over N minus I over J. So K over L times R, getting a common denominator, is going to be N times J, and then we'll have M times J minus N times I in the numerator. Furthermore, you can multiply both sides by the reciprocal. We've already shown that K is not 0, so we're good to go. So we will get L times MJ minus NI all over N times J, and then we have our K going on too. Okay, well, it's the same old deal, right? Actually, we'll do one more step. We'll say R is equal to L times M times J minus L times N times I over K times N times J. And then what do you think we need to show? Good, we need to show that L times M times J minus L times N times I belongs to the integers. That is by closure and K times N times J belongs to the integers, and actually we'll do it separately. Belongs to the integers. That's by closure again. And K times N times J is non-zero, and that's by that handy dandy zero product property. Thus, R is a rational number which contradicts the premise given that R is irrational. Therefore, what was the statement? If A and B are rational numbers, B is not equal to 0, and R is an irrational number, then A plus B times R is irrational. And we're done with that proof, and we're done with the lesson. So I hope you have a wonderful afternoon, morning, evening, late night, whenever you're watching this. And if you like what I'm doing, please subscribe. Bye.